Vlad has told me that I should start without him. So it's good that Alex mentioned the words fluctuation dissipation, because this will come back here. I will talk today about what we know on dynamics of spherical spin glasses. And I could mention, in fact, also other things on dynamics of Langevin dynamics of spin glasses with continuous spins. It might be, in fact, I will give some well-known equations that had been derived at the physics level and introduced first by Laetitia Cugliondolo and Jorge Courant, and that we derived with Amir Dembo and Alice Guillonnet some, I don't know, 7, 8 years ago. And they are a first approach in this thing on spin glasses to this question of fluctuation dissipation. So fluctuation dissipation, so FDT theorem, FDT is fluctuation dissipation theorem. So spin glasses are, in fact, a good problem to study situations where the FDT breaks down. But what Alex was explaining is also a very good situation where to see where a region where the FDT breaks down. So what is the FDT? It's really an interesting thing that essentially every physics student that starts in dynamics learns the FDT. And every mathematics student or professor doesn't know what it is. So there's a gap there. And formally, the fluctuation dissipation theorem says, so you have a dynamics of a system. If you, let's say, for the moment, a reversible system, the kind of things we're looking at here. And by the way, the random walks on trees that Alex was looking at are, in fact, reversible. So imagine that you act on your system at some time. You do something to your system. Then the system responds, and so what the physicists would measure is the response function, which is, so if you act at time t, and then you look at the system at time s, you look at the response of the system to the excitation you gave to the system at time t, so this will be the response function. So that's one thing. And then you have the fluctuations of the system, right? The correlation, for instance, between the system at time s and the system at time t. That's a fluctuation type of thing. Okay? And the fluctuation dissipation theorem says something like, very roughly, the derivative of the response function is related to the correlation. Right? A priori, these are two very different things. One is how does the system fluctuate? The other is how does the system respond to an external excitation? Right? So in what Alex was explaining, it's clear. So what is the excitation? Is the bias. You push. You push. How is the system responding to that? The response function is the speed. And the other thing, of course, is the fluctuation. The fluctuation is just the fluctuation of the position. And then this is measured by one parameter, which is the diffusivity. So it's true that if you think of it, it looks really interesting and not obvious that the size of the fluctuation at equilibrium, here at the null recurrent state, in the thing that Alex was explaining, is related to how fast the system will move, that is, how it will respond to an excitation out of this equilibrium. Right? And that's the Einstein relation. So of course Einstein did it a long, long time ago in his 06 paper, one of his 3 magic papers of the same year. And of course, but not for random walk on trees, it was on a more regular medium. And as Alex says, it gives access to something which is very hard to measure, which is the size of the fluctuation, because it's much easier to respond. What physicists always measure is our response function. You do something to your system and you look at how it responds to it. Now, so why would that be true? So how do you teach the fluctuation dissipation theorem to a young physics student? Because that's always one question one should ask as a mathematician. How did that young physics student understand that very quickly and that we take 30 years to understand something which is... the reason is that the physics teaching is through very simple examples and then just hand-waving generalization. So the very simple example here is the following. If you want to think in terms of the... I didn't really think of that I would talk about that, but let me do it. If you want to think about the fluctuation dissipation theorem in a simpler situation, you do the following. Take a measure on R, say the real line, or RD, which would be the Gaussian measure, and now take the natural dynamics for that, the Langevin dynamics for that. That is the Ornstein-Uhlenbeck process. So you have Brownian motion in a quadratic potential, if you want. So you have a linear force, a linear bounding drift. This is equilibrium. All right. And now you look at this system and you ask yourself, so you have, of course, here one parameter which is the strength of the drift, right, that you put here. And you see that here it's perfectly clear that the strength of the drift and the size of the fluctuation at equilibrium are very related. It's a trivial computation. And now on this thing, which is purely a Gaussian computation, you can compute everything you want. If you act and you put a little nudge to your system at a time, you can very easily understand what happens later and how this affects the fluctuation, right? And so that's how they compute that. So what is the domain of validity of this general phenomenon of FDT? It's not trivial. And it's only after we understood, after this work, in fact, I will be talking about with Amir and Alice, that we saw all this literature in physics about the breakdown of the fluctuation dissipation theorem, that then Amir, in fact, embarked in this project with Jean-Dominique Deutschel to try to write something which seems very elementary, which is what are the conditions, the abstract conditions for the FDT to be true. And so they have a very nice paper in, I think, the Annales Henri Poincaré a few years back, where they give this in a very abstract setting. When is it true? And of course, in all these things, when you have random media and complicated things, then it's not clear a priori that it is true. So how and in particular, you see very well, if you imagine that the derivative of the response function, here the derivative of the speed, is related to a diffusivity, it's a little difficult when the derivative becomes negative. Negative diffusivity is something strange. So a term is missing clearly there. And what is that? It's interesting to understand. And so how do the physicists get around this breakdown of the FDT, in particular in spin glasses, but in many other hard, slow dynamics of, when the landscape is complicated, like this tree? What they do is the following. The fluctuation dissipation theorem doesn't say that the derivative of the response function is equal to the diffusivity or to the fluctuation. It says that it's proportional to it. And the constant is given by the temperature. Right? So when these two numbers are not related by the temperature for spin glasses, the physicists simply say then their ratio is the effective temperature. And then suddenly the relation becomes true, but you replace temperature by effective temperature. Right? When you say that the ratio is equal to temperature, and then suddenly it's not equal to temperature, you define it as temperature, and the theorem is true again. This looks, what I'm saying here, I'm making fun, it looks like silly, but it's not, in fact. It's very interesting. And already last time I kind of hinted at what would be the notion of effective temperature in spin glasses. And that's, in fact, the good way to think in terms of physics, in fact, here. But we don't really know how to do that, in fact. If we could do that, probably the whole understanding of dynamics, know from first principle what should be the effective temperature, that would be really interesting. But I can tell you what it is in words. And we've seen that in the dynamics of the trap dynamics that I've described before. Again, it's the idea that I've already mentioned. At a certain time scale, you explore a certain depth. This we've seen is true. But we don't know it from first principle. I cannot simply say, it's clear that it is true. But you, at a certain time scale, exponential constant n, you, in the models I've explained before, you explore a certain depth, or if you want a certain microcanonical ensemble, certain energy level, right? And, but you've done a certain number of steps, and it's as if you were at equilibrium, but for a temperature which is not the temperature you're running the dynamics in. And this is, I explained last time that this temperature was beta divided by square root of rho in our models we had. So when I say that the regimes we've been studying are out of equilibrium, in fact they are not. They are at equilibrium, but at a different temperature. And so the fluctuation dissipation theorem should have this effective temperature in it. But remember, this effective temperature now depends on the time scale, right? The longer your time scale, the deeper you are, and your effective temperature changes with your time scale. Right? If you have exponential Cn, the temperature depends on C, this effective temperature. So the fluctuation dissipation relation changes with the time scale. Right? So that's a little tricky. But if we could prove that a priori, all this thing on dynamics would be much easier to understand, because then we could relate, as I explained last time, the dynamics and the statics, what we have about the Parisi formula, then we could maybe use some information about the statics there. All right, so enough for this. I wanted to mention this fluctuation dissipation theorem, because in fact here I will talk about response function now. So I want to talk about dynamics of spherical spin glasses. So now you all know what this model is. So I'm looking at the spherical spin glasses. Mixed p spins as always. So here I will, so that these are our classical friends here. I will take only a finite number of them for reasons I don't want to detail. And here the sigma is on the sphere of radius square root of n. Okay. So now I have this function, and you remember I described its complexity depending on the mixture, this complicated smooth function in the sphere. And I want to run, and so I have the Gibbs measure given by this Hamiltonian, and I want to run dynamics that will be reversible with respect to that. Okay. So what kind of dynamics can I do? So the Gibbs measure, remember, was simply this thing. Normalized. Okay. And I want now to run reversible dynamics for that. So last time when I was on a cube, it was kind of simple. I had a cube and I used simply a Glauber type dynamics. The only condition I needed was, so I looked at the continuous time Markov chain, and the only condition I needed was detailed balance, which I explained last time. The jump rate, right, multiplied by the Gibbs measure, should be equal to the jump rate multiplied by the Gibbs measure when you take the sites in reverse order. But here, what kind of natural dynamics do you have on the sphere? I will not look at a continuous time Markov chain. So the natural dynamics, of course, are diffusions. So you want to take, the natural thing to do here is to take Langevin dynamics. So you see, we're all talking about the same period, Einstein, Langevin, all this happened at the same time. So what are the Langevin dynamics? It's simple. A priori, you want to do it will be a diffusion whose generator should be simply 1/2 of the Laplacian minus grad of the potential here, h. So I have a beta h grad. That should be the natural dynamic. Let me explain what this is. So this should be the generator of this. This Laplacian should be the Laplacian in the sphere. And this, of course, gradient should be the gradient in the sphere. So if you take this thing, then it's clear that this guy here will be this measure is an invariant measure for that. Right? That's a general feature. If you take on a manifold, here the manifold is the sphere. If you don't like the sphere, think of RD. If you take a potential H, if you take this kind of thing, Laplacian minus gradient of a function gradient, if the drift is a gradient, then the measure exponential minus this thing is, of course, the invariant measure for that. Right? So that's a very natural dynamic. So what is it? If you didn't have this term, this would simply be, the dynamics generated by that would simply be the Brownian motion on the sphere. And then here you add a drift. So what is this drift doing? If you don't have this just explores the sphere like a Brownian motion. And the invariant measure will simply be the uniform measure on the sphere. If you want the Gibbs measure at beta equals 0, at infinite temperature, which of course happens if you put beta equals 0 here. Now if you don't have this term, this thing will simply be a drift, a gradient dynamics. It's not random. It would simply mean that you take a particle and what you simply do is you follow the gradient. Right? Follow the gradient and then you will end up. So remember, this landscape is complicated. You have lots of critical points. You will end up at your nearest critical point. That's simple dynamics. When you mix the two, of course, you don't stay stuck at at one critical point, because the Brownian motion pushes you out of this well, and then you keep exploring and you go down and down and down. All right. So since this is a class on probability, I don't expect everybody to know enough differential geometry to use the mechanics of this. So what we'll do is I expect that you understand what a diffusion, a Brownian motion, and all that is on Rn, maybe not on the sphere. So I'll shift everything to the sphere, to Rn by a simple trick. Instead of taking the spherical model, I will generalize a little bit the model, but everything I'm saying here, we didn't write it in this context, but would be true on the sphere, on this hard sphere. I will introduce this soft spherical constraint. And then this will allow us to, it doesn't change much, but it will allow us to use just the stochastic calculus on Rn instead of a manifold, which is probably easier for most people. So what is our measure? Our Gibbs measure, oh, I'm sorry, I forgot the d sigma here. Right. This was the Gibbs measure, of course, here is a continuous measure. This is the uniform measure on the sphere. So let me introduce now this soft spherical constraint. I will look at the following measure, my Gibbs measure, okay, x and sigma are the same thing, will be my exponential minus beta h n of x. But I will have here a measure nu n dx, where nu n is the following. So this x now is not in the sphere, it's in Rn, right? So I'm looking at a model on the whole of Rn, continuous soft spins. For the moment, it's not constrained to be on the sphere, right? But how do I kind of constrain it to be in the sphere? I force this measure nu n to be, so exponential minus n, a certain function f of 1 over n norm square, Euclidean norm square, and then I have dx here. And of course you have to normalize this. Maybe I should normalize here. Okay. So what is this thing doing? And so imagine, this f will be something like f of rho typically. Think of it as being, it could be whatever, but think of it being something like this. Right? And this r would be larger than whatever, my m, which is over there, or m over 2. R is large enough. So what is this? First, don't put any random Hamiltonian. This measure here, of course, tends to concentrate the place where f is small. Right? F is small, in fact, f is 0 when rho equal 1. Right? So this f is like a potential in the radius. So when this is equal to 1, so this tends to concentrate on this equal 1. But this equal 1 is exactly the sphere of radius square root of n, right? So this is a soft spherical constraint. Instead of saying I impose strictly that the radius that this x squared is n, I put a weight on it, right? And now I'm working on a kind of spherical shell, if you want. And so I want this constraint to be hard enough, that's why I want this R to be large enough. And now you turn on the random Hamiltonian, right? So it's really the same kind of model than over there, except, you know, if you replace this F by Dirac mass at 1, or the contrary maybe, it's 0 at 1 and infinite elsewhere, then you would have a hard constraint. Okay? So that now is simpler because now I'm looking at a model on Rn. Right? So this of course can be written, this new Gibbs measure can be written as, it has the form exponential minus something. Right? You can write it here. It's exponential minus beta hn minus n times this constraint here. Then dx normalized. Okay? So it's now on Rn something of the form exponential minus a certain potential V. So you know how to construct the Langevin dynamics for that. How do you write this? Again, you take now the same generator. So the generator should be 1/2 of the Laplacian, now the Laplacian on Rn, minus the gradient of this thing. Right? So what is that? Let me write what it is. It's the following system of stochastic differential equation. Each spin now, which is x, xit, depends on t, and it's simply dwit. That's Brownian motions, independent Brownian motion. And minus f prime here of, so I should take the derivative of this with respect to the ith derivative of this. I'm supposed to take the gradient of that. The gradient, the ith coordinate of the gradient is the ith derivative. What is the ith derivative of this? You have an f prime, then x squared over n, of course. And then you're supposed to differentiate that with respect to the ith coordinate. So this is xi squared, you differentiate, you have a 2, xi, and then you have a 1 over n, which kills this n. Right? So here what you get is xit, and so because the derivative I should have, it's a half of the gradient here to have the right thing. This kills the 2 that is up there. dt. So this would simply be the Langevin dynamics when you don't have any random Hamiltonian, right? And when you have the random Hamiltonian, now you have to differentiate this. So you have a minus or plus, whatever. Yeah, minus gives a plus. Beta times something that I will call, okay, I can write in fact, beta over 2. Ith derivative of hn of x. Okay, so that's the interaction term. That's the thing that feels the random potential. Okay, the random Hamiltonian. And you're interested, so this is the natural Langevin dynamics. These guys have this measure as an invariant measure. And you're interested in the long time behavior. So now the question is, so you have this dynamics, xt. It's a diffusion in Rn, but it's a diffusion in Rn. So this is a diffusion in Rn. In a random potential, right? In a random environment. Right? Because we have a random H here. Right? And you're interested in the behavior of this thing. So this is the exact same problem as the one I described last time when I was looking at Glauber dynamics. Right? I was on a discrete structure, I was looking at a Glauber thing. Now I'm a continuous structure, I look at Langevin thing. But here you have two types of questions. I mean, there's a question of what limits, what type of asymptotic regime are we looking at? Because you have two limits here. You could let the size of the system go to infinity. We had the same thing last time, in fact. And you can let the time go to infinity. The regime, if you study this on an interval of time, 0t, the time go to infinity. So remember what we did last time on the cube. We looked at, so on the cube, for cubic models, we took our t as a t of n. Right? And it was either exponential Cn, a constant in n, or exponential little o of n. I gave you the two regimes. Right? So we looked at time scales which were, depending on n, which were very long. Here, what we'll be looking at is different. Here, we will look at first n go to infinity, and t is fixed. And then t go to infinity, if we can. So this regime seems completely different. This regime, in fact, is a short time regime. Right? You're looking at short time. And then when you do that, it's long short time scales. Right? That's the shortest of longest time scale, of long time scales, if you want. I'm not giving, if you do this, when t is fixed, when t is not a t of n, it means that as soon as you have an energy barrier that diverges with n, you'll get trapped by it. You won't be able to cross it, right? So in this time scales, there is no possibility for metastability with diverging barriers. As soon as there's a diverging barrier that you have to cross, since the time to cross it is essentially exponential of the height of the barrier, then you can't cross it. Right? So this time scale seems ridiculously short, right? Because you expect to have, barriers to cross. So, but that's the way the physicists have been studying this regime. And Courant and Parisi, and I remember very well, vividly asking Parisi, but what's going on here? How can you expect this to have anything to do with anything? And he said, yes, that's the right regime to study. Why? I mean, you don't teach Parisi that an energy barrier takes time to cross. And the reason I've already given you, if you now think of what I told you about the complexity, remember, there are two classes for spherical spin glasses. What I call pure-like and what I call full-like. And the idea is that when you are in the pure-like case, this regime here will not allow you to get close to equilibrium because you have traps. But it will allow you to get close to this point, which I call E prime infinity, which essentially going down to that point in energy was possible without crossing barriers. We never proved that, but that's what we prove is compatible with that. Okay? So the idea is that, in fact, you should reach this very low level, negative n e prime infinity in energy, in a finite time. So this could be possible. And that's why, in fact, that's what the physicists call the dynamical transition. Right? They say, and what that means is that this is the regime that you can reach dynamically. But for the full case, in fact, what the physicists expect and what our picture with Stuka, let's say, does not confirm but indicates might be true, is that you can get down to the equilibrium without crossing large barriers. And then this regime should be useful. Right? So here's now that I've said all that, here's the picture that a few years back Giorgio Parisi wrote for me on the blackboard, but he said, I don't get it. How do you expect this to tell you anything? He said, yeah, but here is how you should see the landscape of energy for when you have full replica symmetry breaking. He said, he drew something like this. And for him, it explained everything. And so he said, so now now we are in a position to understand what this is, right? Because, if you are in something like this, you can go down and, if you zoom here, you see something that might do a little bump. But this bump is small here, doesn't diverge with n. So maybe here you have a large barrier, but you can go down without ever crossing a barrier. And so you can do that in finite time. That is the regime where you have. So the way he explained that, he said, let's imagine that you have a potential well. And of course, we're at n dimensions, so it's hard to draw. And to this, you add a little sine function. When the slope is very high here, and you add the sine function, of course, you would see something like I was saying here. Tiny, tiny barriers. And then at some point, when the slope becomes less large, this thing begins to do things which are real traps. Right? This is exactly what the picture with Stuka explained, of course, in heavier mathematical terms. We said there was a E prime infinity, a certain level below which you had traps, and above which you didn't. And what we said is that this level, in fact, was absolutely not there at all in the full case. In the pure like case, you had something like this, and in the full case, you kept something like that. Don't ask me to draw that. I don't know how to do it. Okay? And so the dynamics of those models should be such that when you start from the bulk, which means somewhere up there, you will go down in finite time in this regime until you get close to that level, which I call negative n in prime infinity in my formal notation. And then this thing will be useless. Then you begin to feel the traps, and the dynamics in this regime should look like Bouchot trap model. What I explained last time for the cubic case. Now you will move between traps. So this should be Bouchot type. Okay? So you should have the two regimes. I'm putting everything together now. Okay? That's what should happen. And when you don't have this regime, for full things, this should allow you to get close to equilibrium. Right? With a little caveat. Because nothing tells us, if you look at the picture that we had with Tuka, when you get, it's possible, nothing excludes, because what we had was exponential. It's possible that the number of critical points of index 1 and number of minima have the same exponential behavior, but maybe not the same polynomial behavior. So maybe you may have some traps, which will not be, and the time to cross them will not diverge exponentially, but so it might be that you need to take time scales here, which are not diverging, or maybe diverging slowly, like a power of n. Right? What we do here is we fix t and we let n go to infinity. And we follow the recipe of the physicists there. All right? So all this discussion is to tell you that I expect this to be relevant. This regime here will be relevant as long as you are above this dynamical transition. And so it should be always relevant, essentially, for full-like things, and not always for pure-like things. And for pure cases, you should then go back. You should, at a certain time scale, this thing should now be described by trap dynamics. Okay. So after this, let's try to understand what happened in this time scale. So by the way, what the work that has been done, so it has been done by Amir Dembo, Alice Guillonnet, and myself, and that's quite some time ago now. That's in 2005, and there has been some progress later by Alice, Amir, and Christian Mazza, but not much. This is kind of stuck also, and I'll tell you where we are. So this is in the regime n goes to infinity first, and t is fixed. The regime that I'm just talking about, which is, let's imagine that t diverges like exponential of n, which is the regime you need to explore the traps, and show that this is something like a Bouchot trap model, this is completely open, right? That's, but it should be true. All right, so what we proved was the following then. So I need to introduce two things. Yeah. So maybe before that, let me explain something else. There was, before that, a long time ago, in 95, there was a work by Alice Guillonnet and myself, and that was when we began looking at these things on spin glasses. That was the PhD of Alice a long time ago. I was too ambitious, and we did the following. We took the dynamics for the true SK, for a product structure, not spherical. We took the Langevin dynamics, and we proved the following. For the true SK, which a product structure, Langevin dynamics for SK, we proved that the empirical measure of the trajectory converged to something. That's a nice result. We proved, so that was for SK model, for the SK model, Langevin. And so I don't want to spend too much time in this. And we proved that so for all those who understand large deviation, we proved this. If you look at the trajectory on a time interval 0t, you look at the empirical measure, this converged when n goes to infinity to some measure, let's call it Q, Qt, which of course depends on beta. And this thing, of course, now is the law of a process. Right? It's a law on this continuous function in interval 0t, which depends on beta. That's the law of a process. We characterize this as we had large deviation, we characterized it as a very complicated minimizer of a variational problem. A certain huge entropy and all that. Hoping that then we will be able to understand the behavior of this. This is completely impossible. I mean, there is a characterization of this. It's extremely hard. So why? And I want to explain why things are easier here. Why? It's because this object is really infinite dimensional. This too. It's non-Markovian. It's something very, very complicated, and we have no handle to understand its long-time behavior. Right? The nice thing about the spin glass, the spherical situation that we're here, is that instead of looking at this infinite dimensional object, following the Cogliandolo and Courant, the physicists told us what to look at. So they said, in fact, so you know this equation, if you want, we have some equation which is for this infinite dimensional thing, which is complicated. They said, no, instead of looking at this infinite dimensional thing, look at only two functions. The trick is look at two important functions, observable if you want, or functions of the dynamics. The first one, which we will call Cn of St, a two-time function, it's something we have already encountered in the cubic case. It's simply the overlap, so I call the overlap of the dynamics at time t and the dynamics at time s, right? And remember, we characterize aging in terms of this. The overlap, of course, I could also look at the distance between these two. So it's simply 1 over n, sum of xit, xis. So it's a very natural object for us. Okay? Now, of course, that's what you want to understand, in fact, really. How does the overlap behave? In this kind of situation, the overlap, of course, is a contraction of this. You can, if you understood well this thing, you would understand the limit law of the overlap. But that's hard. The important thing is that it gave us the idea to look at what would be called here the integrated response function. So now that's where we talk about the fluctuation dissipation theorem, and it's the following. This is crazy because this is, okay, forget this. This R is not the overlap. Okay, this one is R is like a response. Okay, so let me erase this. The definition is here. So it's also a two-time function, and it's 1 over n, sum from I equal 1 to n of WIT XIS. Okay? That looks like a strange object that we want to look at. Or maybe, no, I would put an S here and a T here, because I will always choose one to be larger than the other. So I will explain, so this is really what should be seen as a response function. I'll explain why. And so this is, of course, on the side of correlation, right? Forget the interpretation of overlap. This looks like an empirical covariance matrix. This measures correlation. This measures response. And there will be a link between the two. And that would be the FDT. But the link between the two is extremely complicated, right? And that's what that is called the Cogliandolo-Courant equations that I will derive. So the idea that what Cogliandolo and Courant told us was, if you look at these two objects, instead of this infinite dimensional thing, you look just at this two-dimensional thing. This will have a limit which will be autonomous. The important thing is this thing in the limit, this couple of things behave autonomously. You don't need to need anything else. And then you will have a two-dimensional system of equations. We have two equations, which admittedly are complex. They are coupled, integral differential, nonlinear, so painful, but at least you have only two equations. All right? And that's the Cogliandolo-Courant thing. So let me give these equations. So the theorem is under some technical assumption that I want to. So under an assumption on the initial, so I take the dynamics that I told you. I didn't say anything about the initial condition. Right? So under some natural things on the initial condition that I don't want to go too deep into, and there's some concentration. For instance, if you start from the bulk, that would be true. Then you have the following. This function Cn and this function, I'm sorry, I shouldn't, I could have kept, this one we call chi-n. Chi is like susceptibility, sorry. So the function chi-n and the function Cn converge uniformly, almost surely, and in LP, so very nice, almost surely in all the disorder, almost surely with respect to the initial condition, to respect to the noise, and with respect to the J's. So we have three randomness here. The couplings, the randomness of the H, if you want, the W, which the Brownian motion which runs the dynamics, and the initial condition. Right? That's the initial condition. That's the thing that runs the dynamics, and this is the J are the coupling, the H, if you want. Okay, so this is completely quenched. You fix everything, you run, and you say these two things converge uniformly to, in fact, non-random things. C and chi, which are two function of two times. And this chi, so this is the integrated response function. So this chi of S and T, we will write as an integral of R of S and U. And with the following properties. So first, the R of S and T is 0 if T is larger than S. So let me explain what this means. This is supposed to be a response function. So if you excite the system at time t, this is when you excite the system, and you try to look at the response at time s, and you look at the response at the time before you excite the system, of course you get no response. Okay, so you need to, the response begins after you've excited the system, not before. And on the diagonal it will just be 1. And we will note K of S, that's a notation, I will note K of S to be C on the diagonal. So that's something that is, you should remember, something that we already have encountered. It's hard to keep everything together, but let's go back to the Dovbich-Sudakov theorem. What does it have to do with here? Remember that what we said was there was this limiting thing, and then it was carried by your ball, and then when everything went well, it was in fact carried by a sphere, right? But the radius of the sphere was not necessarily 1. It could be a little less. That's exactly what we're looking at. This is the radius of the sphere, right? But dynamically now, not statically, at time s, right? Because CSS, if you look at what it is just the radius of the sphere. Okay? So of course here it's natural that this radius moves in finite time like this because we never fixed the radius in my thing. It was not 1, it changed. So okay, now this is an object that will play a big role, and then here are the Couglie-Andolo-Courchan equations. So this chi and C satisfy the following equation. So they are the derivative in S of R and S and T is minus F prime K of S R of S and T plus beta square, the integral from T to S, so T is smaller than S here, of R U of T, UT, R S U, nu second of C of S and U, du, and that's for R. So you see it's already a painful equation because it's nonlinear, integral, differential, and it's coupled because you have C here, and you also have C hidden here. Then you have an equation for C, which is dsC is minus F prime of K of S C of S as before of ST, this is at ST. And then you have plus beta square, the integral from 0 to S of CUT, CRSU, nu second of CSU du, the same nu second. So remember what nu is. It's the model of the thing that gives us our model of random Hamiltonian. And then you have beta, another term, 0 to T of nu prime of CSU, R of TU, du. And you have an equation for the K, which is ds of K of S is minus 2F prime of K of S plus 1 plus 2 beta square integral from 0 to S of psi of CSU RSU du. And I still need to tell you that what psi is. So psi is a function that we have already encountered, and I think I called it theta before, but psi is nu prime plus R nu second of R, something like this. Yeah. So psi is also a function of defined by the model. All right. So these are the Couglie-Andolo-Courchan equation. All right. So how do you work on that? So of course, this theorem, the hard part is to derive the fact that you have this limiting thing. So these equations look bad, but they are in fact very nice. Because again, you see that in the limit we have equations which relate, this is the fluctuation dissipation theorem. These are equations that relate the response to the fluctuation. And this is autonomous. You don't need to need anything else. You just need to know these two things. People are not directly interested in the response. They are more interested in the behavior of C of ST, but that's, which is the overlap. But you don't have an equation here. You don't have an equation which is autonomous for C. But in fact, you do, if in one case, which was studied before, so there's one case which is much simpler. So that was the case where P equal 2, where your nu of R is just R squared. Right? The Sherrington-Kirkpatrick model in the sphere. So that was studied by the usual suspects, Dembo, Guillonnet, and myself, earlier. It was in 2001 or something, or 2. At this point in time, we studied completely the static, the dynamics of this model, and we proved aging for it. But of course, now we understand that this model is trivial. Because remember the question, what I gave you about in the work we did with Stuka, the complexity when P equal 2 is trivial compared, and where P is larger than 2, then the complexity becomes hard. So the landscape becomes complicated when P is 3, but not when P is 2. So remember why? Because when P is 2, our random Hamiltonian is just a quadratic form on the sphere. The number of critical points is just 2n. It does not explode exponentially. You have two local minima only, and they are in fact the global minima, and that's all. So on your sphere, you essentially have one basin, and you go down. So it's not at all something of the same nature. So this should be seen as being simple. If you look at these equations and you plug nu equals R squared, they should simplify. Right? Otherwise, something's wrong. And they do simplify. Of course, that's in this paper we didn't go through that to then simplify. We did it directly, but that's true. So if you take nu equals R squared, you find the following. If you define h of st to be r of st, exponential integral from t to s, of course t is always smaller than s here, f prime of k of u du, define this function, which is an integrating factor for the equation over there. Then you plug that in the equation over there. So plug in the Coughlin-Dolo-Courchan equations. And after some integration by parts that I don't want to do, you find the following equation for h. You find ds of hst is in fact beta square integral from t to s of hut hsu du. So trust me, this is just calculus. Right? You take this, you plug that over there, you find this. What's good about this? This is now one equation. You don't have two. H satisfies an autonomous equation. Right? You don't have C and chi or C and R. You just have H. So this thing, this R, satisfies an equation that you can explicitly get. Once you know this H, of course you know the R, and if you plug it into the C, then you have an equation for C. Right, which is autonomous. So you can first solve for R and then for C. But more interesting, this equation exists in the literature. And magically, this equation, the solution to that, this H you can find is simply, we call it L of beta s minus t, where this function L, so you can find the solution to this, and the function L is what? Lo and behold, L is in fact the Laplace transform of the semicircle distribution. So you have an explicit, so why is the semicircle distribution here? So you remember what the semicircle distribution, right, is. So semicircle distribution, sigma of dx on the line is just square root of 4 minus x squared dx normalized, right? So it's this probability distribution. That's the semicircle distribution. You compute it Laplace transform, and this gives you the solution here. So why is this coming here? Okay. So of course we noticed it because we had work on random matrices with Alice. The Laplace transform of the semicircle distribution, when you see it, you realize it's there. But so why? Of course, because when you have p equal 2, when p equal 2, the trick to do everything here is simple. So that was the first case. When p equal 2, remember, the Hamiltonian is simply this. Right? And these guys are 1 over square root of n. And these guys are IID and 0, 1 above the diagonal, let's say. Or symmetric, if you will. So this is a quadratic form. So of course you can diagonalize it. This you can write as sum of lambda I ui square. Right? Well, the vector u is some g, or maybe not g, because some O times the vector x. Right? O is an orthogonal matrix, because this is a real symmetric matrix, which you can diagonalize in an orthonormal basis. So O is an orthogonal matrix, which in fact here is chosen uniformly, randomly, under the Haar measure on this orthogonal group. This is purely uniform. And these guys are what? The lambdas, which are the lambda i's, are the eigenvalues of the matrix of the Gij divided by square root of n. Right? Which is exactly the matrix which we call the GOE, the Gaussian orthogonal ensemble. So the spectrum, so what is well known, which goes back to Wigner, is that the spectrum of this so it's well known that this converges to the semicircle once properly normalized. That's why the semicircle is there. So what is our model here? You have this spherical model, you change the basis, right? This is a random transformation, but you change the basis. In the new basis, the Hamiltonian is completely decoupled. Right? You had exponential sum, exponential of the Hamiltonian becomes now a product. Exponential of sum of lambda ui square. You have random axes, but once this is fixed, it's purely a product structure. Right? You have independent modes. So that's not too hard. Right? And the strength of the mode is this, the lambda I. And the distribution of these converges to this thing, which you find here, which is not a big surprise. Maybe it's hard to track down why they would come here, but it's a fact. Okay? So in this model, what happens is the following. Here is how you should think of it. This is a trivial model. There's no complexity, p equal 2. You don't have a complicated landscape. Essentially, you have one deep well. In fact, you have two. Right? You have two minima for the sphere. A quadratic form has only two minima on the sphere, which are antipodal. So essentially, you cut the sphere in two. The minima correspond here to lambda 1, if you want, the smallest eigenvalue. So then you take a point at random, and what will it do? It will fall in. What you have over there is, on the sphere at least, you have a quadratic potential. So you will fall along this quadratic potential until you get to the end. But what makes this interesting is that it's possible. There are these lambda i's are random. So in fact, what will really play a role is the edge of this distribution, here. The small eigenvalues, right? Because these will describe the curvature of the bottom of this quadratic well, right? If you have a quadratic well, the curvature is given essentially, the Hessian, if you want, given by those lambda i's. And so you will have directions where this well is very flat. And when you have enough directions where where this is very flat, then the time it takes to get down is very slow in those directions. That's aging. in this context, which, as you see, has nothing to do with the aging I described before, which was how do you move from one well to the next. Here it's a much shorter time scale. Is how inside one well, how do you get to the bottom of it? Right? It's a completely different phenomenon. All right. So let me describe a bit more what we know in this case. So in this case, once you diagonalize like this, in fact, the equation, so you rewrite the equation, the Langevin dynamics, in the new coordinates. In the new coordinates, after you diagonalize your matrix U, and then things are much simpler, and you get something like this. dUT is lambda I UIT dt minus f prime of 1 over n norm u square. The nice part about the orthogonal transformation is it doesn't change, of course, the Euclidean norm, so it doesn't change this term. And then you have minus, I must have missed a beta somewhere, plus dWIT. So why is that not changing? I had a Brownian motion. But if I act by a rotation on the Brownian motion, I still get a Brownian motion. It's a randomly rotated Brownian motion, but it's still a Brownian motion. Right? If you take Brownian motion on Rn, rotate it, it's still Brownian motion. Right? So this equation is way simpler now. It's trivial, in fact. Maybe I should put it. Why? If you didn't have this term, you see this is purely Ornstein-Uhlenbeck. Right? But without this term, this Ornstein-Uhlenbeck, half of it would explode. Right? Because look, these lambda i's are distributed like this. So if I didn't make a mistake with the sign, which makes no difference because this is symmetric, when your lambda is positive, right? If you have a positive, half of the lambda i's are positive. When you have a positive mode here, in an Ornstein-Uhlenbeck, this explodes. It's a drift that pushes to infinity, right? So, bad luck. But, of course, now you have this guy, which pushes back in. So, that's why we chose this f to be like, here it would be like r minus 1 to the power kappa with kappa large enough, or I don't know, r with r large enough. So this will be superlinear in this case. So this will kill this. So without that, of course, this Ornstein-Uhlenbeck would be, half of it would explode, and half of it would disappear. This thing will essentially compensate for all that. But that's where you see the possibility of a phase transition. Depending on this beta, so if you want, let me put that very vaguely. If this thing overcompensates for all the lambdas, then this thing just, if this f prime kills the contribution of all the lambdas up to here, then okay, you have fast convergence to equilibrium. You will have naturally fast convergence to equilibrium. But then there will be a point where, depending on this beta, where this guy just barely kills the exploding mode, if you want. And so this will be the critical temperature. And when you begin to have this, then things will begin to be different. And you see that what will be important is the edge. Because this will happen when beta will, the first lambda that you will feel have an influence are the largest one or the smallest one, depending on the sign. So what will be important is the behavior of the semicircle distribution at the edge. And this is well known. We know how this behaves. Right? So once you put all that together, and then you will see that something else should happen there. And this is what we find. So let me explain this. So this will depend very much on the initial condition, but I will first describe the most natural thing. So let's take the initial condition. That's the case 1. The initial condition to be taken, so the x0 to be taken IID if you want. I could take them, on a sphere. That would not make a big difference. So randomly, I don't choose something specific. So formally, I start from the bulk. Right? In this case, what we find is that we find something explicit that I could write, which. So let me introduce the following thing. This one-dimensional object maybe a beta here, and call nu lambda the law of this, then what we will see is that the distribution, maybe I don't want to write all this. Let me skip to that and go to the conclusion. Let me say simply that we can prove that 1 over n, sum of, in fact, we even have a large deviation result. This thing, this empirical measure, converges to something, let me call it Q of t, as I'd explained before. But this Q of t is very explicit. This Q of t is simply a mixture, depends on beta, a mixture of forced, nonlinearly forced Ornstein-Uhlenbeck processes. And I don't want to say much more than that. But it's very explicit. And with this, we find the following, the consequence, which tells us the long, so now, if you want, here what we've done is let n go to infinity, understand the limiting dynamics. We have an explicit expression for that. It's a mixture of simple things. Again, for a very simple reason. Look at this. This is if you don't have this, right? If you do the following. Replace this by a constant. Imagine that this converges to a constant. And this becomes a constant. So now you have a large constant that you subtract to all these guys. Oh, and I forgot the UIT here. So this large constant comes with the lambda i's. Now you have here negative modes, and this will be an Ornstein-Uhlenbeck. Right? You have negative constant UIT dt plus Brownian motion. This is an Ornstein-Uhlenbeck. It's an Ornstein-Uhlenbeck, but it's mixed. It's a mixture because these lambda i's are random. So you mixed randomly different Ornstein-Uhlenbeck, and that's it. So when I said force here, it's because this thing has to be large, right? So you really push it. But with this now, you have two things. So there exists a beta critical. So now we can try to study what happens for large time. So that when beta is smaller than beta critical, which is high temperature, then the covariance, so remember what that is. This is the overlap again. This is the limit. So remember what this is. This is the limit of 1 over n, sum of xis, xit. Then this thing will decay like a constant time exponential minus another constant, t minus s. So this means that this decays exponentially. Right? So what does that mean? You look at your trajectory, and it forgets its past very quickly. The overlap between the trajectory at time t and at time s, later than t, goes to 0 very quickly. These 2 points their overlap go to 0. That means they just completely forget where they are. They're as if they were chosen completely randomly. There are two important things here. This goes very quickly, but it also only depends on t minus s. It's time translation invariant. It's not like aging. So if I chose s to be larger than t, that was s minus. Okay, absolute value, so then I don't have to care. But then you have the situation where beta is larger than beta critical. We also study the critical thing, but let's forget it. And then what you find is that this thing now behaves like a certain function, which is in fact s over t to a power q over 2. This q here is linked to the exponent here. So here this Q is a half, if I'm not mistaken. Right? So this is this is aging. Now this tells you the overlap at two different time is a function of the relative duration in terms of the age. It's S divided by T. So in order for this overlap to become small, you need to wait a time. Oh, so here, let me see. Which one is smaller than the other? Here it looks like I choose S smaller than T. Okay. No, it can be what. No, S is, no, that's good. S is larger than T. Whatever. I can't remember that. But what it means is that, so let me see, when S goes to infinity, this Q is positive here. Or is it? How did I choose that? Yes, it's positive. So I should put a T over S. That would be better, probably. Okay. So this means that in order for the overlap to become 0, you need to wait time which is long in terms of the age, right? So, and this is a completely different aging than what we had before. There's no arc-sine law or whatever. It's just linked to the fact that you have these Ornstein-Uhlenbeck thing, and a few components will have a very small mode, so they are mixing, but they mix very, very slowly. If the mode is very small, then they mix very slowly. Right? That's what this tells you. Okay, so that was when you start from the bulk. Now, when you start, you could also look at, if the initial condition is, of course, this is just a little ridiculous, but start from the top eigenvector of our matrix, or the bottom of eigenvector, I don't know which one. Here, the bottom eigenvector. Right? Then, of course, there is no aging. Then this CST, when beta is larger than beta critical, converges to a constant, which is usually called Edwards-Anderson. Why is that? Because if you start from the bottom eigenvector, it means you start from the bottom of the well. Right? The well is, in fact, the minimum is at the top or the bottom eigenvector. So if you start from the bottom of this thing, then you don't have aging, which corresponds to how fast it takes to get there. You start from there, and you get something which is a constant. Right? That's the completely different thing. And finally, if you start, what you can also do is start from, but maybe I won't describe this, it starts from the stationary, the invariant measure. Right? And there, so if third condition, if the initial condition is, if you are really at equilibrium. So the model is so simple that you can study everything. If you start at equilibrium, then what you see that this CST converges to a certain function C of T minus S, which is natural. It's equilibrium, so it will be something which depends only of T minus S. And you cannot have an aging. So here that you have no aging, and here you have no aging too. Naturally, because you are at equilibrium, you can have aging. So the aging happens when you start from your initial condition. So the physicists would say it like this. When you start from an initial condition which is IID or taken from the bulk, it's as if you were starting from an initial condition which is sampled from the Gibbs measure at very, very high temperature. So you do what they call a deep quench. You start, and then you run at a lower temperature. And then it takes time for your system to get to the right temperature, and on this way to there, the way you explore the space induces aging. If you start from something which is at the right temperature, right, you start from something which is typical for equilibrium, then you don't age. Right? This, in fact, consists in starting at 0 temperature. This is starting at infinite temperature. This is starting at 0 temperature. You start from the minimum. Right? And this is starting from the right thing. So if you start from 0 temperature, you go to a constant. If you start from the right temperature, you go to a function of T minus S. And if you start from something which is very high temperature, then you have this aging phenomenon. Right? This kind of picture, of course, which we can prove here only for the spherical p equal 2 case, which is trivial, there should be something of that nature in general. Right? And in fact, if we understood more, we could look at many more things that physicists say. They don't simply look at this. They don't simply look at, let's launch the system at infinite temperature, put it at low temperature, and look at what happens. They may start at temperature T1 or beta 1 and run a temperature beta 2, and then do cycling in temperature. Suddenly raise the temperature again, and then they would see what they call rejuvenation. Your system ages and it becomes young again, and then re-ages and this kind of thing. We are very far from being able to do things like that. So this is this very simplest case of p equal 2, which, as we understand now, is really not typical of what happens later. So now, if you look back at the general case now. So again, what is known on this Courant equations in general? So very little. So what you expect is the following, that for this, when you take this Courant equation, so now it's a problem of PDEs, if you want, or integral differential equation. It's no longer statistical mechanics. You have one set of equations, try to extract information from them. Of course, we obtain those equations as a fixed point of some large transformation, but in the end, you have the equation in front of you, you should be able to do something with them. So what you expect is that at least something of the same nature that what I wrote there. You should have a critical temperature, which is dynamical temperature, above which, this C, the overlap, which is one of the two terms of the equation, should also decay exponentially. That's what you expect. So, right, that should happen. And you also expect that at large enough temperature, at low enough temperature, this should behave like a certain function, let's say phi, of S over T, or T over S, I don't know what I said here. Right? So when when temperature is low, you should expect something like this. When S and T are large enough. You should expect this to be a function of T minus S when T minus S is not too large. Right? But when S and T are both very large, you should expect this to be like a function of T over S. This cannot be proved. But what do the physicists do? What Ghirlanda and Courant do? And their followers. So Ghirlanda and Courant derived this equation in the 90s, I think, in 91 or 2 or something like that. And we proved them mathematically 10 or something years later. What they do is, what you can try to do is plug in the Ghirlanda-Courant equation an ansatz of the form C of ST is a function of either a function of T minus S or a function of S over T, or T over S. Right? You can try. I can try a time translation invariant solution, plug it in, and then find an equation for phi, and you do the same thing for chi. Or you try something like an aging solution, like this, plug it in, find an equation for this phi, and then see whether you can do something. Right? So when you do that, you find equations for phi, and same thing for the two-time function chi, from which you can predict aging. You can see that a function like phi of t over s behaves like a t over s to some power, of course not the same q, is compatible with the equation. You put that in the equation, it works. So of course, the first, and same thing for the response function. So of course you would be tempted, if you work at the level of physics, to say that's the aging behavior for these models, right? But even at the level of, so first, I would not expect that to be, of course, we expect a different type of aging if you have traps, or if you don't have traps, in different time scales and all that. But this is short time aging. But this cannot be proved. We have tried very hard, and we couldn't do that rigorously. And in fact, when you talk to Ghirlanda and Courant, they realize, and they write it, that they cannot do it either. For the following reason. Their problem is very ill-posed. They realize that, in fact, there's this what they call the matching problem. The idea that if you do this kind of ansatz, you see that you could, in fact, essentially end up with any solution you want. There's an infinite group of invariants which makes your problem not well defined in terms of the initial question. So everybody's stuck. They don't know how to choose one of the solutions. Even at the level of physics, usually that doesn't happen. Usually they tell you, yeah, we have plenty of possible solutions, but we know this one is the right one because of whatever. That we don't have, right? So the behavior of this, for Ghirlanda-Courant equations, so for the long-time behavior of spin glasses, spherical spin glasses, except in the trivial case, we don't know, right? So there are many questions open. We don't know this. We don't know what would happen in larger time scales where you would have traps. And I'm sure there is something very interesting happening even when you have traps, when you get close to this dynamical transition. Because then suddenly, if you remember what I was drawing, you begin to have traps, but which will be small. They will be run by Tracy-Widom type fluctuation of the spectrum. And when you have small traps, not yet microscopic, not like n, but maybe like n to some small power, then the behavior will become also very interesting. So all this is totally open. Right? And this has been open since, we had this equation, these equations are derived mathematically since, now they've been around for 7, 8 years, and this doesn't move. Right? So there is probably something to be done there. I'm not saying that this is easy, so maybe this is to be taken with care. So I think I will, I'm a bit early, but I'll stop here. Yes, but before that I want to thank IMPA for this. This was a great time for me, at least. And I want to thank Vladas for that. That was really a fantastic time. And I hope that some of these questions will be solved next time I come to Rio.